Professor Vestroni will introduce the next keynote.
It's a great pleasure, an honor to introduce Professor Steve Shaw. For people of my generation, Steve Shaw is a very well-known researcher, but for the most younger people here, I would like to remind some steps in his career. He started in Cornell and with a PhD in theoretical applied mechanics, and he wrote the first paper with Francis Moon, Holmes, Wiggins, Rand, Settner. Also many papers by himself, because this is the rule some time ago. And also he received honors from some interesting paper with Hedo and many others. He received honors from American Society of Mechanical Engineering, especially the Koge Dynamical Medal, and he wrote a lot of contribution. Not so many papers, but any paper quite interesting, and from theoretical and applied mechanics. But his name is a little bit related, linked, bound on about nonlinear modes, topics where we have a lot of contribution from the past, from 60s to now, and he gave a very important contribution because about the extension of nonlinear modes to non-conservative system. So it's very appreciable choice of chair to invite Steve Shaw to talk about nonlinear normal modes using invariant manifold and so on. Thank you very much. Please.
Thank you. Thanks, Fabrizio, for introduction. And that's a picture of the institute I'm at now, where you can watch rocket launches. There were more than 60 in 2022, and so it's a very active place. Moving on, first I want to thank Walter. Here's a picture of us in Lyon last summer, where we talked about this subject, and he suggested this keynote, so I'm very grateful to him. And of course, I'm very grateful to my collaborator in this work, Pierre. There's a picture of us also in Lyon last year. Christophe has reemerged after years of administration to back into technical work, and which is great to have him back. We benefited from some grad students and postdocs who did most of the heavy lifting for this work. Also, this is a subject I haven't worked in for 20 years. So this is a historical talk. I knew the history before that, but I wanted to survey people who were there working in the area before me and looking at things since. So there's a list of people here who I contacted and had discussions with, and and contributed a lot of information to this, this talk. So I'm going to talk about some preliminaries, things that are very simple, and I'll go through them quickly because this community knows them, and then talk about the real foundation of this whole area, which is a result from Lyapunov, and then Rosenberg style normal modes, and then the invariant manifold. That's the main part of this story. And in recent developments, where I spent a lot of time talking to people and reading papers, and then I'm going to speculate about what's next. So here we go, linear vibration modes. We teach this, if you have a very simple conservative system with symmetric mass and stiffness matrices, these modes for a simple 2-degree of freedom system are straight lines in the configuration space, x1 and x2 for a 2-degree freedom system. And one of the key properties of them is if you start with an initial condition, say on either mode, it will stay in that mode for all time. Of course, if you start an initial condition, so that's the orange and blue. If you start an initial condition, say black, then you get a combination of modes, superposition. But the invariance is an important property. And in fact, it extends to a subset of modes. So if you have n degrees of freedom and you say start initial conditions with just 2 modes, it'll stay in those 2 modes. There's no modal interaction in these cases. Now, the thing is that for these vibration modes, when you have these straight lines where x2 is proportional to x1, And the mode shapes are of this form where you just have essentially a vector in the configuration space. These are applicable for undamped systems or systems with damping, so-called Coggy damping, a very important paper by Coggy back in the 60s. And the modes in these cases are the standing waves, the classic string vibration where the nodes are fixed and the antinodes are fixed, but the vibrations occur. And the key properties of these are that there's a unison motion where all degrees of freedom simultaneously reach zero and their extreme values. And this is what was generalized by Rosenberg. We'll talk about that in a minute. But of course, for this to happen, all the degrees of freedom in the system have to have the same frequency. And the full system, in this case, behaves like a 1 degree of freedom system. So it's just a simple vibration, but for a large dimensional system. So these are things we know about linear vibration. But what happens when you have non-Coggy damping? Non-proportional is the standard way, but more generally non-Coggy damping or non-symmetric mass or stiffness. For example, in a gyroscopic system, we have a rotating shaft or things like this. Then it's known that you need to go to state space formulation. You need to use not only the displacement system, it's a second order system. You need to use displacements and velocities. And so you end up with a state space model that has two end states. And the formulation of the modes, instead of being just x1, x2 proportional to x1 and so forth, you actually need a matrix. Let's say you need a set of matrices, but for a 2 degree of freedom system, you say that the degrees of freedom, x sub j and x sub j dot, are linearly related to x1, say, and x1 dot. You need some guiding mode to have it, have this happen. And so if you formulate this way, you can see that this generalization requires complex, happens when you have complex eigenvalues and complex eigenvectors, where the eigenspaces are the span of the real and imaginary parts of the eigenvectors. And instead of modal lines, you have modal planes. Now, this is really, even for a 2 degree freedom system, you have a 4-dimensional space. So to represent a 2-dimensional surface, you need to have these two surfaces I've shown here, where you have, say, you can just think of it as x2 and y2, which are the displacement and velocity of the second degree of freedom, which depend on the displacement and velocity. Now, what are these? These are surfaces, and they're now invariant surfaces, and I'll show examples of this, but the point is that if you start with initial conditions on these constraints, it will stay there for all time. And that's, and the key there is that you go back, so that instead of standing waves, now you have traveling waves. So the motion is no longer in unison. We saw during the musical performance these golden waveforms going by. The nodes were not fixed, the extrema were not fixed, and so in these systems you have it. Of course, usually they're damped out, but the point is you no longer have standing waves. So this is known. This has been known. So in terms of an overview, in nonlinear dynamics and linear vibrations, we're interested in these problems in periodic motions. Of course, you can get quasi-periodic motions in both cases. It's more interesting in nonlinear dynamics because you can get them from nonlinear interactions rather than just summation of modes. I won't talk much about localization, but those of you who know localization, it can occur in both systems. And of course, you have chaos and no chaos, no superposition, superposition. Those are, to me, a couple of the key differences. But you do have invariance. So I've talked about invariance in linear systems, but invariance in nonlinear systems, it's a general concept, and it's very simple. Look at a set of points in a state space or phase space, and ask yourself, if I start in that set of points, say a surface, or you can higher dimensional, and you run time forwards and backwards, if you remain in that set for all time, that's an invariant set. And so obviously these linear modes on the straight lines are invariant, and the surfaces are invariant. But this generalizes, I mean, so far we're talking about fixed points, but it can be limit cycles, tori, and so forth. What we're going to be interested in here are invariant manifolds. A manifold is nothing more than a set that locally looks like Euclidean space. But we know that if you look at a linear system and you look at a fixed point, for example, you have eigenvalues with positive, negative, and 0 real parts. And there are eigenspaces associated with each of those. They're essentially the span of the eigenvectors associated with those 3 cases. There's theorems. It turns out that the stable and unstable eigenspaces, shown here in green and red, the dashed lines are the eigenspaces. There's a theorem that says locally there are there's smoothness conditions, a lot of things. But the point is that there are invariant manifolds that are tangent to those eigenspaces at the equilibrium point, and that the nonlinear system is invariant along those stable and unstable manifolds. Those, of course, are higher dimensional. This is just a cartoon. And for the stable and unstable manifolds, there's actually a theorem that says they're unique, and they exist and they're unique. But as we're going to see, if there's submanifolds within these, those may not be unique, and that's going to be an important part of the story. In the center manifold, when you have 0 real parts, it's been long known that these are not unique. So submanifolds is something we're going to talk about. So suppose you just look at a 2-dimensional stable manifold, and you have 2 eigenvectors, say u1 and u2, and you have submanifolds, say this w2 and w1 are the submanifolds associated in this overall stable manifold. The key is that these submanifolds, even though this whole stable manifold may be unique, these submanifolds may not be unique. And this really came into play in developments, later developments in nonlinear normal modes. But the story really starts with Lyapunov in the nonlinear story. So he proved his subcenter manifold theorem, which essentially said that if you have an n-degree freedom system with one constant of motion, it doesn't have to be integrable. In fact, it's more interesting when it's not. But you have a certain non-resonance condition on the frequencies, avoiding things like equal frequencies or 2 to 1 or 3 to 1, that there exists local to this fixed point a family of periodic solutions that lie on a 2-dimensional invariant manifold. So it just looks like a family of closed circles or closed ellipses local to that fixed point, and that they approach the linear response of that mode, that oscillation mode, as the amplitude goes to 0. Now, you may think this is a topic that's not active, but you can see in the middle figure here, there's a paper from 2018 where the authors actually prove that this theorem generalizes to the case of weak dissipation. So that's just a new result. It's not some, and of course the spectrum on the right is the case we're talking about, where we have purely imaginary, we have a set of natural frequencies. That's the case we're interested in. Now, this was picked up by engineers. There's a book, Kauderer, which is available only in German and Russian. And actually, I don't have a copy of the book, but Valery Polipchuk, who's here, was kind enough to send me some pages with notes. Kauderer actually predates Rosenberg. Rosenberg generalized what he did. Kauderer actually mentions a 52 paper. Valery pointed this out to me that suggests a similar formulation. So this idea goes back to the 50s. But Rosenberg is the one who really pushed it ahead. And he said, well, look, he built on the simple version of linear vibrations, motion in unison, and said nonlinear normal modes of a system, so I have an n degree of freedom nonlinear system. If every degree of freedom passes through 0 at the same time, reaches its extreme values at the same time, that's the definition that he used as a nonlinear normal mode. And in fact, it's interesting, you can go back to a 1959 paper where he was thinking about the stability. He actually did a stability analysis for these modes and confirmed it using analog computers. He had a series of papers with collaborators, and as is true with a 30-minute historical talk, I'm going to skip over huge batches of material, but I'll point to some literature along the way. So, Rosenberg nonlinear modes, motion in unison, and there's a lot of work done on so-called similar nonlinear normal modes, where x2 and x1, or xj and x1, are linear related like linear modes. But in general, a non-similar mode, he said, well, look, let's like x2 as a function. We're going to make it some nonlinear function. And we'll talk about this in a minute. But the key insight, one of the key insights that he had was that the number of nonlinear normal modes can exceed the degrees of freedom. Not true in a linear system. And these come about because of instabilities and bifurcations. The other feature of this is that when you construct the problem the way I'm about to show you, you determine the mode and then the dynamics. And the resulting dynamics are those of a single degree of freedom system. I'm going to emphasize that F2 of X1 is not enough. You need to have the energy in there. You need to have a conservation of energy, and you need to put energy in there. Now, Rosenberg's work was extended by Minevich, Miklin, Filipchuk, Avramov, Rand, Vakakis. There's many, many papers. And lots of work on similar modes, non-similar modes, and so forth. But there's an interesting story that Alex can tell about meeting the Minevich group and them collaborating and discussions on a train and so forth. And what came out of that was this book by them about normal modes and localization on linear systems. If you want to start anywhere in this subject, that book has, up to 96, has a very thorough background. There's also some review papers by Avramov and Miklin, 20 and 2013, that cover this, Rosenberg, but other. And it turns out that Konstantin and Yuri visited Christoph and I, and Valeri's near us in Wayne State. In 2005, the five of us were together for a few days of discussions. So that was a connecting point. That was after Christoph and I had done a lot of our stuff. But anyway, so you need conservation of energy. These next few slides are a bit technical with equations, but for a 2 degree of freedom system, you have, with a potential V, the forms of equations of motion are given, and you want to figure out a system where you only have 1 degree of freedom, and the other degree of freedom, x2, is constrained to f1, to x1, I mean. So to do this, you're going to need to eliminate somehow x2 double dot from the second equation, and if you look at the chain rule, you end up with a just simple application of the chain rule. You end up with x1 double dot and x1 dot squared. And the way you get rid of these, eliminate them. Oh, one of my circles got off there. Sorry about that. But you need to deal with x1 dot squared, and you do that by the energy. This is where the energy comes in. You write down the energy, you impose the constraints, you get an equation that involves h, which is the constant energy, x1 dot squared, and x1. So you can solve that for x1 dot squared. For x1 double dot, you use the potential, and you push all that through, and you end up with an equation that you solve for. It's an ODE for f, and most of the papers up to this point were all about the properties of the solutions of this equation, which is very interesting, but it involves the energy. And then, once you find f, you have the normal mode vibrations by the x1 equation. You've eliminated time. It's all done in the configuration space, but you need energy. Key question, how do you handle cases for which that is not sufficient? In other words, you don't have conservation of energy. Well, this is the point I think is most interesting from my perspective and in the development of what Christoph and I did. First of all, I was at Cornell as a grad student in the early 80s, and I knew about nonlinear normal modes from Richard Rand. I didn't work in the area, but I knew about them. He was working on them. In '89, I went to sabbatical at Caltech and met Alex Vakakis. He explained all this beautiful stuff he was doing, and I asked a kind of simple, naive question. Well, what happens when there's damping? And he gave a very plausible answer, but the techniques rely on conservation of energy. So how can nonlinear modes persist? They must. You can't just destroy that whole picture with small damping. Around the same time, Christoph and I were discussing localization. I was learning about mode localization, and I said, well, you have to have a definition of nonlinear modes, and there's this Rosenberg definition, but we started thinking about a generalization of Rosenberg nonlinear modes, and so the question is, what are the key properties if you're going to extend it? Well, really the answer is invariance and single degree of freedom systems. So you want it invariant. It has to go on a 2-dimensional invariant manifold. So your whole state space restricted to some 2-dimensional invariant manifold. It doesn't matter if there's damping or whatever, that will give you a nonlinear mode. So you need state space. That was the bottom line. It's just like with linear vibrations. You need to go to a state space formulation. Instead of x sub j as a function of x1 and h, you say x sub j and x sub j dot are functions of x1 and x1 dot. And then you no longer need energy. So these are surfaces. So here's the cartoon picture. A nonlinear normal mode is a two-dimensional manifold. So Rosenberg's picture of these curves and configuration space become pictures of two-dimensional manifolds. And the linear systems analogy carries over. Instead of a line, you get a 2D surface. So here's our original definition. Christoph and I, we said it's a motion on a two-dimensional invariant manifold that passes through the equilibrium, and it's tangent to the eigenspace for that mode. And it uses state space, and it's based on constraining all the degrees of freedom in the system to a set of guiding single degree of freedom states, which I'll call U and V, but energy is not used. We really should have called it the nonlinear mode the family of motions on that invariant manifold, a little technicality. But the one thing that our picture overlooked is that you can have more, this restricts it to just extensions of those modes of the linear system. And of course, we know there are others. And a lot of people have worked on that sense. So again, a few technical slides. You write the equations in first order form. This is a special form that comes out of second order systems, of course, where you have x double dot is equal to something. But you take the guiding states as the first degree of freedom. Of course, there's some restrictions about that, but it works for most cases. And then the key is that the constraints are that all the degrees of freedom are going to track U and V, and that's the dynamics of U and V will give the nonlinear mode dynamics. So it's the same spirit as Rosenberg. And the idea is, so now, how do you do it? Well, you take time derivatives of the constraints. I'm doing it for 2 degree of freedom systems. You use the chain rule. And it turns out that you know what x2 dot, capital Y2 dot are in terms of U and V by substitutions. You know what U dot and V dot are from the equation of motion for the first state. And now I'm going to show you a crazy roadmap, but essentially you plug all those in and you eliminate time. And this is standard stuff that we do for invariant manifolds. You're doing center manifold calculations for bifurcation analysis and so forth. It's exactly the stuff that is done that way. But the point is you end up with a pair of PDEs for, in this case, for capital X2 and Y2. Remember, capital F1 and F2 are the forces in the system. And lots of solution types. I mean, series expansions, what Christoph and I did first initially and naively, but there's numerical solutions. There's lots of ways to attack this problem. And the key is that once you solve them, I'm going to talk a little bit more about, because the perspective of how you solve them has been recently enhanced by the math community. But once you solve them, of course, you go back to the first guiding degrees of freedom, and you just plug in the constraints, capital X2 and Y2, and for little x2 and y2, and you get a single degree freedom, essentially a state space form, or in second order form in terms of the U variable. And this is totally, I mean, not totally general, but it's very general. It can include damping, non-proportional damping, gyroscopic effects, lots of different things. So here, I'll show this is just a toy problem that Christoph and I worked on. It was just to demonstrate that it works. There's the mode 1 dynamics on the top right, and the bottom is the initial condition on the invariant manifold, and you let it run, and of course it works. It's invariant manifold theory, unless you've made the calculations. Now I'll show a more interesting example that we came up with that really demonstrates what a nonlinear normal mode is. It's a simple beam, and notice that the spring, the support spring, is what's known in the community as an essential nonlinear. It has no linear part. So the linear vibration modes of the system are the linear vibrations shown there. They're the sine waves of the beam, sine wave shapes. And so what we do is project this PDE onto the modes. Of course, from symmetry, for example, the top and bottom on the lower right are going to involve the spring, so those will be nonlinear. But notice that the even modes have a node there, and so those will be linear modes. So I'm going to show some animations. These are ancient animations, 30 years old now, more than 30 years old. So I hope they look all right, but you pick the primary states to be the amplitude and velocity of the first mode, and my animations don't work. Let's see if I Nope, the animations don't work. Maybe is there a button you can try anything over there? Because they worked on the screen over there. If not, I can describe what's happening. On the left, so both the beam things, both the beam pictures are going to be the same animation. On the lower left, there's a red dot, and it's actually the third mode. It's the third, oops, okay. It worked on the screen over there 2 hours ago, so my apologies. What we're showing in these surfaces is the third mode contribution. Oh, there, if you click on that, that should do it on the play button there. Nope, okay. It shows the third mode contribution to the first mode, and the red dot will run around, and on the left, it'll stay pretty close to the plane. This is small amplitude. So on the right, the invariant manifold is pretty flat. The red line there is a length reference because I'm going to expand the size of the phase space. You can see this is oh, this one works, beautiful, okay. So now you can see, well, the right one works. The left one, you can see, all you need to see is that the red dot is away from the linear mode. And so as it tracks around, it keeps tracking. You see the shape of the beam flattens out, which is the third mode contribution to this nonlinear system. And it makes intuitive sense. The key is this analysis is a systematic way to tell you how much of that happens. So that's really an important one there, because the next one is just a larger amplitude. That's fine. You can see the linear eigenspace does not capture the dynamics. If you were on the right, of course, it stays on the nonlinear mode manifold. And these manifolds are constructed by power series, which works for this up to a certain amplitude. Now, here's the thing, that these are the peak shapes of the beam, which involve first and third modes. And the system state at peak, shown there in red, you can see that the third mode contribution increases as a function of amplitude. But one of the keys is the green, that this surface depends on the velocity of that first mode in this formulation. So you cannot use a Rosenberg single curve to capture this. Now, the thing is that the system state moves on the manifold. It gives you the shape and the dynamics. So we worked on this. We did piecewise linear systems. You can read it here. I think one of the more interesting ones is that we did continuous systems. We did finite elements very crudely. Other people came along and said, hey, especially in honor of Ali Nefe, he said, you know, you can do all this with multiple scales. Okay, yes, you can. And he did a great job, and he used complex variable formulation, which is very elegant. At around the same time, Jezekel and Lamarck were doing normal forms and relating it to this kind of work. But what came next is parameterization of invariant manifolds. So the next developments, I don't have time to talk about most of these. Localization, experiments, system ID. I'm going to talk a little bit about reduced order modeling and normal forms, but only I'm going to focus on the bottom two, which are really zoom in on how you compute invariant manifolds and nonlinear modes. Parameterization. The math literature is back to 2003 up to 2016, and even that paper I showed you in 2019, that math literature was picked up. And basically, there's two storms. There's two styles. There's graph style, which Christoph and I did, and Rosenberg. You get the mode, the dynamics are a consequence. You can also, when you do normal forms, and there's several people that worked on normal forms, you simplify the dynamics from the equation of motion, and then you get the modes as a byproduct. So, groups by Haller and Touzé Olivier and so forth used this applied math literature to develop, in George Haller's case, spectral subspace modes, and the French group did direct parameterization of invariant manifolds. So the thing is that they both provide efficient computation of invariant manifolds that work. You're going to see I hope my animation of the next slide works. You'll see how impressive these are at computing invariant manifolds that fold back on themselves, which power series can't do. A useful review, very recent, 2023 in nonlinear dynamics. Stoichev and Rumer is a very thorough review of these methods. And I would say if you want to know what the state of the art in this, that's a good paper to look at because it covers all of the recent developments. Good, this animation is working. This is courtesy of Olivier and Cyril. And They've got a great review on model order reduction. This is a clamped beam with 1 to 3 internal resonance. This is on the right is the mode 4 dependence on the mode 2 displacement of velocity. And on the left, it's tracking out the backbone curve going through an internal resonance where it loops around. And this manifold folds back on itself, and these methods are able to compute that. And it goes up and comes back. It's extremely impressive. So I thank them for letting me show this animation. Non-uniqueness of submanifolds. From a paper by a group at Bristol in 2014, made a common observation that makes sense when you think about it. When you have zero damping and non-resonance, Lyapunov says the submanifolds are unique. But as soon as you add damping, if you have strong damping in one direction, say on the left in the vertical direction and on the right on the horizontal direction, all of those manifolds are tangent, and any one of them can be picked as the mode manifold. So how do you pick it? They're not unique. So in this paper, they recommend the use of normal forms to avoid these non-uniqueness issues, and they do very elaborate and detailed and interesting calculations to show that. But George Haller said, well, wait, let's do a different way. He essentially defined the spectral submanifold as the smoothest of all those possible, which is a way to make it unique. And this is computable in cases of comparable, and important for cases of comparable decay rates. And on his website, here's this right from his website where he's doing a cantilever beam, showing the invariant manifold, showing actually the going along the backbone curve. He does forced damp response. He has an open source tool that does first order form, works with finite elements, quite general type of nonlinearities, smooth nonlinearities. But one thing, and here's another 2023 paper that I think is important, and I'm going to close with this analysis that George has been working on in his group. Existing approaches all use power series for integer powers, x squared, x cubed, and it's taken us a long way. But George was doing simulations on that original damped system that I showed that Christoph and I did 30 years ago, and playing with the damping ratios, he couldn't get them to work. And the problem was that the mode coupling, because of the damping ratios of the two modes being comparable, and I won't go into details, but he analyzed it and found out that for the backbone curve, which is shown here in the middle equation, you need fractional powers of the amplitude. In this case, beta over alpha is the ratio of decay exponents, and if it's between 1/2 and 2, those are lower order powers. And it turns out these terms are always present in the normal form, but usually the coefficients are either very small or the exponents push it out where they're not useful. So Haller's paper that just appeared last week in Chaos, he analyzes this. He actually even does data, in our time now, he's doing data-driven methods to get spectral submanifolds that are valid over a large domain. And what motivated him to do this was actually experimental work with the University of Wisconsin, where they were looking at vibrations, force vibrations of hydrogels. And in the middle plot, there's different response curves, frequency response curves, and a backbone curve that comes in, and it doesn't come in vertical like it has to if the nonlinearities are smooth. And you try to fit a nice backbone with integer powers, and you can't make it work. So what's the answer? Fractional powers. This backbone, this normal form with these fractional powers, you actually measured the two decay rates of the two modes that are coupling, that are interacting, and you can get this non-vertical tangent at the origin at very small amplitudes. I think this is something interesting because it's not something we generically see and think about, but there's a paper by Renson from IMAC 2021 that shows evidence of something like this. But really impressively, on the right is a paper from Nature Physics where they're actually measuring the gravitational interaction between two beams as they're vibrating. Real gravity. It's not easy to measure gravity. That's why we have LIGO. And these are extremely careful measurements where they can account for damping and everything, and they see exactly this behavior. So, I'm going to wind up by saying I actually made a list. I started making a list of books and review papers. It took up 3 slides. So I can share them with you like. But just the literature in this area is vast, and it goes all the way back to Cowder's book in '59, all the way to papers in 2023. And what's next? Well, Stoichev and Romer said we shouldn't pick invariant manifolds by smoothness, we should pick them by how well they represent the low order dynamics. Data-driven methods, I ask questions here. Will analysis tools be standardized? What happens when the system doesn't have a nice eigenspace? I know people are thinking about that. But it seems like nonlinear modes, when I was talking to Alex and Gaetan Kirshen and so forth, and all different people, they said, look, system identification, experimental testing, optimization, computational method with MEMS. There's a lot of papers on computational method with MEMS out of the French group. These are all going, they're playing, nonlinear normal modes continues to play an important role there. And there are sessions here at this conference where you can go and learn more. And I apologize for not covering more in limited time, but there's a lot of literature and important topics. And with that, I'll close. Thank you.
Question, comments?
I can talk about it.
Thank you, Steve, for this comprehensive presentation. Very interesting and stimulating comments, question.
Everybody wants to talk. Go ahead and give them the mic.
Thanks for an amazing talk. Thank you so much. I just have a question. It seems that the approach boils down to a set of PDEs. Yeah. So any thoughts on the existence of solutions of these PDEs and whether Frobenius' theorem can provide any insight in this regard?
Okay, so okay, now it's working. Okay, so I haven't worked on the existence and uniqueness. These mathematicians have worked on, there's a lot of results in there, because those math papers, the applied math papers, and I can provide references, they're very detailed in terms of fundamental development and using those results, how to compute things. And that's why the French group and the Swiss group have picked up on that and essentially used it. But so I would check those papers. The thing is, you know, as engineers, we're computing them. They give great dynamics on the reduced order model, so that's the engineer's answer. The more applied math answer, I'd say check the literature.
So the submanifolds that you talked about, most of the time it was two-dimensional in nature. But when you have situations where you have a three-dimensional or a four-dimensional manifold, and won't the PDs become too complicated? Or
well, I mean, they're being computed for large-scale finite element models. Olivier, how big are models? 10,000 degrees of freedom? Yeah. So they're two-dimensional manifolds, or in some cases four-dimensional manifolds that are projected, you know, from these high-dimensional state space, and they solve those PDEs numerically, of course.
Okay, so numerical solutions.
Numerical solutions, yeah. Yeah.
Any other comment? Question? No comments?
People are ready for coffee.
Just a comment. Probably you listed a lot of interesting future points for the maintaining this importance of nonlinear normal modes. But what do you think about that lines are the most results that we are going to take advantage in the future?
You mean which of these are most important? Probably. I would, okay, so I think this, the first two are important. I think they'll drive everything else. I would say the essential nonlinearities is interesting from an academic point of view, but I think like the first two will drive things because they will decide how practical things are for things like system ID and so forth. So I think data-driven methods and how you pick the nonlinear. The first one, I think that there's a lot known about it, and it's not clear that choosing one invariant manifold over another when you have non-uniqueness, it's not clear that that's that important, but we need to think about it. So, and then the applications will keep driving it. If people aren't doing applications, system ID or MEMS with it, and then it's not worth, I mean, it's only academic then. Anyway, sorry, thank you.
Thank you very much again to Professor Steve Shaw.
Yeah, thank you, Steve. Your job is not over because now you will write a paper, of course, on history of nonlinear neural modes.
I'll get Chris
Your
involved.
second feature article.
Okay, thank you, Walt.
So thank you again.